thanks for this opportunity to talk to you about some of the activities in my team. I will be summarizing 4 to 5 recent papers in my lab. So I guess I have about 45 minutes, right, Stella?
Yes.
To go through this. Towards the mechanistic understanding of adhesive, where this is work that started in my team about 5 years ago with Ramin Aghababai. He was a postdoc, now he's a faculty in Denmark. Derek Warner is my first student, in fact, at Johns Hopkins. He's now a prof at Cornell, and he came to EPFL on sabbatical 6 years ago, and he worked with Ramin on this topic. Then was Tobias Brink, another postdoc, now back at Max Planck in Germany, and also students, PhD students, Enrico Milanese, who just finished his PhD, Luca Frero, finished about 2 years ago, a year or two ago, and Son Famba, who is a current PhD student. Okay, so I like to start this talk with a seemingly very, very naive question on what is friction and how do you measure it? And it turns out that it's not at all naive. It's not at all an easy topic. And for this, I'm turning to this extract from a VAMAS report where, and you can read this, that basically this agency, this organization provided identical steel and aluminum oxide to various labs around the world with everything was controlled, roughness, ambient temperature, sliding velocity, load. So everything is controlled. And they ask those experts labs, so really people that who know what they are doing, they are experts to measure the friction coefficient. And that's the data that came back out of this report. You see here the friction coefficient. Those are country names. F is for France, J is for Japan, and you have those stars. This is data from specific labs in a given country. And you find a wide spread of values from 0.9 to 0.3. This is a huge spread because the friction coefficient is bounded between 0 and 1, supposedly. So you have tremendous variations. So there are many good reasons why measuring friction is challenging. It's not well understood. And I like also to cite this scientist here, Jan van de Snopschot. He was, I guess, if I remember correctly, the Wikipedia page, he was a computer scientist at Caltech in USA. And he got crazy at some point, by the way. He wanted to kill his wife with an axe, failed to do that. He burned his house, his wife and 3 kids could escape, but he died himself in a burning house. So he said, and I love this sentence, in theory, there is no difference between theory and practice, but in practice, there is. Okay, so measuring friction is challenging. And why this is the case? So this is a bit a disclaimer slide. I'm taking this figure from a review paper from a group of colleagues. And this slide is meant to scare you. You see that you involve at a frictional interface, you have a huge variety of chemistry and physics taking place. And it's a disclaimer slide because, in the modeling that I will present later on, I will forget about a lot of the mechanisms you have there, and you will be able to criticize me saying, no, you forgot about, the effect of temperature, you forgot about lubrication mechanisms, and you'll be absolutely right. So this talk is about third body generation for the most part, and where related to third body generation. Okay, so there's huge variety of mechanisms, and physics and chemistry explains why it's very hard to come up with predictive models of friction. And because of those different mechanisms, you have also a huge variety of scales and modeling techniques that you can use to look at a frictional problem. So, and depending on what you choose, you will have some advantages and disadvantages. So you may choose to work at the very large scale, at the scale of engineering components of a tire and a road, and for this, for instance, you may resort to finite element modeling, and you will be able to model very large system sizes and large time scales. So the time scale is the vertical axis here, but you will miss, obviously, physics and chemistry from a smaller scale. For this, you could go to ab initio simulations, but the drawback, of course, is that you give very small system sizes and time scales. So there's no free lunch. Okay, another complexity that comes when you talk about understanding friction is that surfaces are rough, and they are rough not a single scale, but at several length scales. And strictly speaking, there's no separation of scales. So I like to show this data from François Renard, he's a geophysicist, now in Oslo, and he's showing us here, he measured the roughness of the San Andreas Fault over hundreds of kilometers, and then part of the San Andreas Fault in California is sticking out of the ground. You see this piece of rock sticking out, and with a laser technique, he measured roughness of this area. Then he cut a piece of rock, put it to the lab, and measure roughness at even smaller scales. And a nice way to represent roughness, often for natural surfaces, is to compute the Fourier transform. So this is this equation of a height autocorrelation function. H is the height at a material point X along a surface. And if you put the Fourier transform, if the surface is self-affine, you find that this Fourier transform is a power law of the wave vector Q with a well-defined exponent. This exponent is related to what is known as a Hurst exponent. H is called a Hurst exponent. And you see that this data of François Renard, you see that you have indeed the power law. This is the straight line. It's a log-log plot, okay? And a power law on a log-log plot is a straight line with a slope here, H, about 0.7. And it's amazing to see that you find a scaling over not 1, 2, 3 orders of magnitude, but over 10 orders of magnitude. You see here, please pay attention to the scale from 1,000 kilometer to sub-millimeter length scales here. Okay, so roughness is important. And a major consequence of roughness is that you develop microcontacts. So here I'm turning to this classic seminal paper from Dieterich and Kilgore in 1994, where they used a transparent material, blocks, transparent so that they could shine through a monochromatic light, and where you establish a microcontact, an intimate contact between the two blocks. At the peak of the asperities, you can transmit the light, but where you have gaps, the light is diffracted. And therefore, we could get direct observations of those microcontacts here for varying loads. And those are those bright color spots. So the major consequence is that because of the roughness, is that the real contact area is much, much smaller than the apparent, or also called the nominal contact area. And this is a major finding that Bowden and Tabor in 1915 used to finally give a mechanistic interpretation of a friction coefficient and explain the Leonardo da Vinci experiment, and later Amontons and Coulomb, who observed that the friction coefficient mu is independent of a nominal contact area, but it's function really of the real contact area. So the mechanistic understanding of Bowden and Tabor is that the total tangential force F is a product of the real contact area times the strength, the flow stress that can carry the contacting asperities. And because the real contact area is increasing more or less linearly with the load at small loads, well, you get this linear relationship between F and N, which is this emerging Coulomb friction coefficient mu. Okay, so another point I want to take home message in this general introduction I want to bring to you is that mechanics matters. And I will go back to this point at the end of my talk. There are asperities interactions. So those are a figure taken from old papers 15 years ago from my first student, Lin Pei at Johns Hopkins, where we made the point of comparing finite element simulation results to what used to be, and still is to some extent, a standard model in a tribology community, which is called the overlap or cutoff model. So at the right here, this right image. So the overlap of cutoff model is a purely geometric model. Surfaces are rough, okay? So here you have a schematic of some surface roughness, and you have this dashed line, and you're going to consider that what is above the dashed line is in contact, and what is below is not contacting. So purely a geometric model. And if you apply the scheme to a 2D rough surface, and here the square is looking down at the contact surface, with this overlap model, you find this kind of bulky, complex geometry, but more or less bulky blue contact. However, if you account for bulk elasticity interactions, when you press on an asperity, you have long-range elastic forces, slow decay, the point force, you know, is decaying as 1 over the distance to the point source, to point force. So it's a slow decay. And you see that if you have elasticity or here elastoplastic contact, when you push an asperity, you bring down the neighboring asperities and you bring up microcontacts into contact that are further away. So mechanics matters, which is good news for us with a mechanics background. So, okay, this was a general introduction. Now I'm going to go to the heart of a topic. I want to discuss wear of materials. So if you think friction is complicated, and it is, well, the bad news is that wear is even more complicated. It's messier. So here I'm citing Ernest Rabinovich. This is his seminal textbooks on friction and wear of materials. And in this book, he writes, all the wear is an important topic. And it is, right? We observe wear in all engineering applications, in our bones, in our joints of our knees. But although it's important, it has never received the attention it deserves. And the reason is that it is perceived as a dirty topic. There's complex physics and chemistry. There's many forms of wear. Adhesive and abrasive wear are the top two. There's history. The roughness evolves with time. You form third bodies. You form gouge, different regimes. And I cite here at the bottom of the slide one of my favorite papers of all time, Meng and Ludema, 1995, summarizing 50 years of research on friction and wear. And in this paper, they give you 300 different equations on friction and wear, some of them with 25 different material parameters and fit constants. So there's a lot of empiricism in the field. And what we aim to do is to go back to the basics of the mechanism, to develop insights and come up with a predictive understanding with no fit parameters of production of wear debris. So that's our goal. It's very ambitious and we'll keep it busy for many, many years to come. Okay, so here I'm turning to the most known and the most used equations for wear. Out of those 300 equations, it's called Archard wear law. Very popular because very simple. So this equation tells you that the production of wear volume V is linearly proportional to the applied load, linearly proportional to the sliding distance, which you can relate to the life expectancy of a component in an industrial machine, and inversely proportional to the hardness of the material. And you have here data showing indeed this linear curves, this linear proportionality. The only problem is that for this theory, and we go back to where this theory emerges from a micromechanics description of why this equation comes to us. But the only problem is to match this theory to experimental data. You need the famous K injuring factor. And this K injuring factor is not a small correction. It's not 20% correction. It's not a factor 2 correction. Hell no, it's not even a factor 10 correction. It's a correction, let's say, of 6 orders of magnitude. So it's a gigantic correction. And we don't know what is K. So to me, it's a major problem. And usually K is interpreted as a probability. Surfaces are rough. We develop millions of microcontacts. And let's say 1 per million will form a debris. And the moment you set a probability, you are confessing that you're playing a mathematical game, you're losing the physics, and it doesn't give you insight of truly what's happening and why and where you form debris. Okay, so when Archard came about with his model in 1953, there were competing theories. So as a caution mark, here in this talk, I will not be mentioning what is known as a small load limit, grazing contact, where N is very, very low. And this has been discussed in the nano tribology committee more recently, where it has been shown that you have an atom by atom attrition. It's a thermally controlled process. You have a breakdown of Archard. So I'm not discussing this. I will be discussing the higher load limits, where we have really strong interactions between asperities. And there, historically, so going back to 70 years ago, there were 2 competing theories. A theory from Holm saying that when you form an adhesive bridge between 2 asperities, here in the schematic, the strong adhesive forces, as you shear your system, they're going to move past each other by plasticity-induced atoms removal. Archard and others said, no, when you form an adhesive bridge, you're going to get cracks and you're going to form a debris. You see it here at the bottom, and you have even evidence of atomic force microscopy that with tips that are broken, and you see a tip that has been broken and that is being attached to the side of the AFM. Okay, so we have two competing theories, and 5 years ago we came up with a theory with Ramin Aghababai and colleagues and Derek. We came up with basically with a model that says everyone is right, so very consensual, very Swiss in a way, where we say both Holm and Archard are right. The only thing we have, in fact, depending on the system, material properties, and geometry, we have a brittle to ductile transition, which has been known in material science for a long time. So the model is very simple. It's basically Griffith fracture mechanics approach. We take a very simple geometry of two hemispherical asperities, establishing a junction of size D. As you load your system in shear, you're going to store elastic energy in the system. It's proportional to the elastic energy density. The elastic energy density is the strength that the junction can carry, sigma j. You cannot go above sigma j because that sigma j will flow plastically. So sigma j puts a cap. Sigma j square over twice the shear modulus is the elastic energy density, and I'm multiplying this by the volume of the two hemispherical asperities, so d to the cube. Okay, so you store elastic energy, and you may use this. That's a second mechanism, that's Archard, to create some new surfaces. There's a price to pay for this. This is the adhesive energy. You create new surfaces. So the surface energy term is called delta W, and it's going to be proportional to the new areas you need to create. And that's why you have a D squared term. And we're assuming that we cut the asperities at the base. It's a very gross approximation, but it makes our life simple. And that's why you have alpha and beta are fudge parameters that are, will not vary the findings by more than a factor 2 or 3. Okay, so looking at the energy map, as a function of D, D is the size of a junction. So it's a geometry. It depends on your roughness of the type of asperities you have that you imprint on the material. So you store the elastic energy. Remember, it depends on D cube. So when D is small, this is a negligible quantity. So elastic energy is money you have at the bank, and you can use it to buy yourself, that's a blue curve, adhesive energy that grows with D square. If I sum those two quantities, I get the green curve. And you see this green curve is initially here positive, then it becomes negative at the critical length scale D star. Below D star, you don't have enough elastic energy to create cracks, and therefore you will flow plastically. That's the left here, this red arrow. To the right of D star, you can form debris. And D star is really a function of material properties. And it gives you this transition from this ductile to brittle mode of plastic flow to debris creation at asperities. So the simple idea has generated a lot of activities in my team, and still does. We'll give you some perspectives at the end of still open the questions, and there are many. Okay, so I will not be discussing much what we did in this paper with regards to comparison with AFM, but this simple equation could explain a lot of discrepant AFM data. I'm just citing here one paper where they discussed this paper that they increase the tip size of the AFM going down, and they reported that they transitioned to plastically dominated wear for narrow tips for large tips that they have brittle fracture dominated wear. So precisely what we are saying, and there's a lot more data we could discuss on this. Okay. Also for the inside story, this finding did not come directly to us. It was a struggle over many, many years. And not only for us, I will say for all the molecular dynamics community looking at wear mechanisms. I can say that up to 2016, all the reported data, to the best of my knowledge, showed the ductile mode of deformation and not the brittle mode of deformation. So here I'm just, to illustrate my point, take the data of Peter Spiker, who was a postdoc in my team 10 years ago. And we did simulations of two rough blocks sliding on top of each other. This is the initial roughness with some self-affine surface properties. We So we rub blocks together, and very quickly you see that we kill the roughness. We develop plateaus, like butter that we cream that we are spreading on a piece of bread. So we lose the asperities very, very quickly. And there's good reason for this. The reasons for this is that to get this brittle mode of debris formation, we need to resolve the process zone size at the crack tip. And this is a large quantity for atomistic simulations. Keep in mind that for this box here, this was a copper material with an EAM potential, and the size of this box was about 32 nanometers. So a tiny, tiny quantity when you think of a typical problem we look at in traditional mechanics. So here, this is an Ashby map. You have different groups of material. Metals are here, you've got rocks here, and this is a fracture toughness as a function of yield strength. And an estimation of a process zone size at a crack tip, the zone where you have nonlinear dissipative mechanisms occurring, well, it's a ratio of a fracture toughness to the yield strength to the square, and this is a large quantity. And I'm reporting values here with those oblique dashed lines. So for metals, it's typically millimeter sizes. For rocks, it's typically micrometers. So orders of magnitude too large for what we can achieve for most materials with atomistic potentials, classical molecular dynamics. So what we did originally to find this brittle mechanism was to come up with model materials that are extremely brittle, so that we lower their scale to domain sizes that we can very quickly solve on our computers to develop this insight. And now actually we're moving back up to more traditional potential, looking at ceramics, and we are able to see this transition at a higher cost, but we can do this. So the original simulations are here. Just to illustrate my point, I'm going to show a case of two colliding asperities. The coloring is artificial, just to see where things are moving. We maintain a fixed pressure. We'll have periodic boundary conditions on the side. We apply a displacement. And what we saw is that if you develop a junction size which is smaller than this star, we observe what everyone else had observed. That is a lot of adhesive transfer from one surface to the other. And eventually, because we maintain the pressure, we're going to close this gap, and we have not formed the debris. Okay, so a lot of plasticity. We are ductile, but no debris formation. So now I'm not changing necessarily here the material properties, but we make the junction size D larger than the star, and something completely different occurs. We get cracks, and you see you start forming a rolling debris, which is incidentally creating a roughness. You don't flatten the surface. Okay? You have a debris with a well-defined size. Okay, so as I said, this has been repeated with more realistic potentials also in a 3D setting, and consistently what we have observed, if D goes above the star, we transition to forming a debris. Okay, so now let me go back to Archard law. As I told you, Archard law requires this unfortunate K factor, which is called the wear coefficient. It varies widely in values. It's viewed as a probability. For us, it's not a probability anymore. If we are at a scale of an asperity, here we're looking at an asperity. If I pick the geometry of asperity to be larger than the star, we know we're going to form a debris, and therefore we have 100% probability of forming a debris, and K is equal to 1. If not, K is equal to 0. So K is not a fudge parameter for us anymore, it's 1. And we can ask the question, do we recover Archard law that the wear volume is N times S over the hardness? So we can ask this question. Just to tell you where this equation comes from, I told you we'll do this early in my talk. I'm here going back to the classic Archard paper of 1953. Okay? It's a very short paper, beautiful mechanistic insight. So we're looking down at an asperity at a contact junction here, and we slide it. And as we slide, we lose the contact after a sliding distance of D. We have lost the contact. Okay? And the wear rate, W, is really the ratio of the volume of the debris you form over the sliding distance. I've told you that the sliding distance is proportional to D, and the volume of the debris is proportional to D cube. So you get a D cube over D. That's a D square. D square is an area. And in Archard model, the area is proportional to normal load over the hardness. Okay, so V over S equals N over H, therefore V is N times S over H. We recover Archard value. Okay, so we try that. We try that because we can control in our simulations the applied load N, we can control the hardness, and we can measure the debris volume V as an output of our simulations. From a debris, we take it out and count the number of atoms in there. And all those points, color points, represent different simulations in 2D, in 3D, different potentials. And you see that we don't find a correlation between those two quantities. Okay, so we don't recover Archard. And the reason is actually very simple. At the core of Archard model is the assumption that the contact area is proportional to N, but it's not for us. And the main reason, and that's well understood in the committee, is that we have adhesion. We're looking at adhesive wear at a small scale. And because you have adhesion, you can form a non-zero contact area for zero applied load N. Okay? So you see, we don't have this proportionality between those two quantities. What worked well, however, in order to predict the final debris volume is the accumulated frictional work. So here I'm showing you some snapshots of a formation of a debris. And in blue, you have, as a function of time, the tangential force. You reach a maximum, eventually you decrease, you reach zero here. And if we integrate the blue curve, I'm getting this red curve. So that's the integral of the tangential force along the sliding path. This quantity, normalized by the junction strength, which is a material property that we control in our system, has, for units, length to the cube. It's a volume. And we have shown in this paper that it's a very, very good prediction to the final debris volume that you have here. We have a correlation, we have a slope of 1. So we thought we were onto something really new. It turns out it's an old concept in a tribology committee. There's a paper from a mathematician and geometer from Germany called Rey, who wrote a paper in 1860 in German. Very, very few citations, a handful of citations, much less cited than Archard. And in this paper, he recommends using the frictional work to predict wear volume. It turns out that if you are at the macroscopic scale, and if you can neglect adhesive forces, you are here on the left. Well, those two models are equivalent. Okay? But what our paper showed, it gives us a means to bridge between scale, to bridge between also to contact at the micro scale or atomic scale where adhesive forces are important. Okay, quickly, just as a opening slide for an open question. So I've told you that we can predict how big particles will be. Well, I should say how small they are, because the minimum particle size we can always form particles larger than D star. But D star set the minimal length scale that you can form in the debris. And I think that's relevant for transportation. We know that air pollution is an increasing concern for societies, and it's less and less due to exhaust pipe. We are moving to electrical cars, and more due to wear of brake pads, of tires on roads, so on and so forth. So here I'm showing a brake pad. That's a new brake pad. We measure the roughness of this brake pad at EPFL. That's a worn brake pad. The roughness has changed tremendously. And brake pads are a very, very complex material. It's a composite with lead, with tar. It's really a mixture. And we do not know what is a minimum particle size for such complex material mixture. Okay, what we have done was a homogeneous material, a perfect material, but now here we have defects, we have inclusions, and that I think still remains an open question. Also, what's intriguing to us, and just one slide to summarize this more recent paper from student in my lab, Enrico, is, and so it's still a mystery to us, but I told you that when we form debris, we observe that over a long time scale, we develop roughness. And we've extracted this roughness for the bottom surface and also for the top surface. And we see how the RMS, root mean square, evolves with time. We reach a steady state eventually. And we try different systems. Some systems that were initially perfectly flat, like this one, except this little bump. We tried also systems that had initial roughness with a well-defined Hurst exponent. And we tried different also mixtures of material, different colors represent different material properties. And again, here we form a debris and we develop roughness. And we've computed the PSD, the power spectral density, as I've shown you in one of the first slides of this presentation, François Renard data. And of course, here we are limited to only 2 to 3 orders of magnitude, because those are very long simulation and expensive. We cannot do 10 orders of magnitude from data in directly observed on rocks, obviously. But what I want to show is that we recover power laws with Hurst exponent very, very close here, h equal 0.7, what is observed with the natural rocks. And the reason is that we have the key ingredient is to require to have fair bodies with 2 competing mechanisms: ductile deformation competing with brittle fracture. And we are, I will not present this today, but we are working on simple geometric model, a random deposition model to try to understand this better. We also trying to finish extracting data, and I will not cover this again, but just a teaser slide where we move from those 2D simulations here to really 3D simulation we could access at the time, which was the fastest supercomputer in Europe. Now I think it's number 3. It's located in Switzerland, in Ticino canton. And with this, we could look at roughness evolution for in a 3D setting. So you see that here, starting from something flat, we arrive at something rough, with again evidence of some self-affine scaling for the surface. And we've also looked at interactions between debris particles. Here we're looking down at the interface, and those are particles that will, as they move along the surface, they're going to, because of adhesive forces, they're going to accumulate mass. So the molecular dynamic simulations again. You see the accumulate mass, they grow in length, they become like French baguette, if you want. They start to attach each other, and you can tell the sliding direction is left to right, at a slight angle. And as they attach, they elongate in one direction. They also start to attach on a side, and this has important consequences on the emerging frictional properties of the system. Okay, so for the last 7, 8 minutes or 10 minutes or so, I want to go back to contact morphology, and I told you that one of the first slides that asperity interactions matter, and I want to give you hints of what we could do to explore this a bit further. And one thing I completely skipped is in this discussion on where is, in fact, interaction between those microcontacts. So it's known that as you increase the load, it's shown on this curve on the right, W is the load, you increase in proportion the real contact area. And as you do this, obviously you start to populate more and more your contact with microcontacts. And it's clear to us at this point that they have to interact, they are nearby, right? They cannot be treated as isolated microcontact. And in fact, there's observations in the literature that where regimes change as a function of load. And it's known that as you increase the load, you transition from what is known as a mild wear regime to severe wear regime. And what I want to give you a hint at here is with the schematic is that as you increase the load, you populate more and more your interface with microcontacts. They start to interact. And perhaps the transition from mild wear to severe wear is the fact that we will form a debris at a single asperity for mild wear, versus for severe wear, we will englobe several neighboring microcontacts with gaps in between. So it's not anymore the real contact area that matters, but it is the nominal or apparent contact area that matters to form a debris. Okay. And we can see this in those simple 2D atomistic simulations where look at this inset where we have 2 contacts occurring in those red regions. And if you shear the system, you see you start to develop shear stress beneath the surface that's tau that develops two peaks in red here at the two disjoint contact. And because both of them have maybe a junction size larger than this star, you form two debris. So that's a later time in the history, you have formed two debris particles. However, if you reduce the space between those asperities, lambda is a spacing, and you bring them very close together, then you realize that you form a single debris that has a larger volume than a combined single debris. And that's because there's elastic interaction. You see the stress peak of a single peak in the stress field underneath the surface. Let me skip this, same illustration in 3D. And a mechanism really that we have observed is a crack shielding mechanism, where at those two junctions, you're going to develop cracks at the corners of our junctions. You have a crack here, second one there, a third one here. You're going to develop a fourth one here at the red regions with high tensile stresses. But this inner crack propagates a bit slower than the outer crack, and therefore is unloaded by this propagating outer crack. And this inner crack shuts down, right? It's healing itself. And therefore we get this one large debris when asperities are close by. So therefore, if you look at the total volume of wear mass that you produce as a function of lambda, the space in between the asperities, if lambda is large, and large, it's basically larger than a junction size D, this is 1 on this axis, well, you will form two debris of mass of size V naught, of volume V naught. V naught is a volume of a single small debris. So you have a 2 here on this axis. However, if lambda gets smaller than D, you transition to forming a severe wear regime where you form a much larger debris. Okay, it turns out there are a lot of interesting perspective also to extend this to continuum models. And here I'm turning to a very nice paper from that Stella has led when she was at Caltech with a student, Sylvain Collet, who worked with her at Caltech. And in this paper, she's using the phase field modeling of fracture to precisely look at this, except that with the phase field modeling approach, you can probe a material parameter space which is much richer and much more precise than what you can hope to do with atomistic simulation, where it's hard to change the plastic properties with atomistic potential, whereas phase field modeling of fracture with a good description of bulk plasticity opens the space for you. So this is just an illustration from this paper, one out of many, to show that in fact, when two junctions are nearby, here you see this image, well, at those high tensile stress regions, at the inner cracks, well, the cracks cannot propagate because the outer crack propagate faster. So she recovered those mechanisms, and again, that opens up a large field. We've also probed this with cannot do this in a plasticity domain so easily, but with the BEM method, boundary element method, where we look here at a single body, and I'm turning to the study from a student in my lab, Son Famba, and I know this figure is too small, but he looked at this in a 2D setting where he basically got an adhesive wear map depending on the space of those debris, where you transition from plasticity dominated to separate the debris versus large combined debris. But what I want to show in my last 1 or 2 slides is moving the BEM simulations to 3D, to 2D contact surfaces or 3D semi-infinite bodies. So here we'll be looking down at a contact surface. We'll apply a shear load Q, and we're going to ask the question of how could we optimize an abrasive tool to basically get the largest possible debris. So the ingredients of this paper, which had just been submitted yesterday, it's on Archive, we are using BEM modeling of a contact problem for elastic interactions. We use metaballs to define the contact geometry. So metaballs have those simple circular domain that define the contact regions. So when field C is equal to 1, we're in contact. When C equals 0, we're out of contact. and we can merge those metaballs very easily. There are two metaballs that are making a more complex geometry, and we're going to generate different initial organization of those metaballs on our plane. You have here some yellow representation of those contact regions, and we have 200 initial configurations, and then we're going to use a particle swarm optimization algorithm to move those places around in order to, that's a bottom bullet here, in order that for a given total force to maximize elastic energy, basically maximize interactions between those micro contacts to form the largest possible spherical debris. And for all the simulations are a different curve. You have 200 of those curves. We find the best solution possible. That's what you have here in this bold dark line. So here, that's an animation of different initial configurations that are moving around trying to find the best configuration possible. And the best solution is this one. Okay, so something that looked like a quarter of a moon of 3 microcontacts interacting, englobing a region, make the convex hull of this that's going to basically succeed to take off a piece of material in between. And I propose here an application for this. So I actually got a patent of this. It's an ice cream scoop application made up of tritive. We actually going to do some testing. We have, of course, theoretical estimates of the energy gain we can get with this, but no one believes the theory, so we have to attach, that's a design of this ice cream scoop that we have 3D printed. We're going to attach this to a robotic arm and really cut through ice cream and see how good they are. So that's our idea of using this for a very, very simple tool, an application. Of course, you can come up with other designs. Here we propose 3 teeth. Others might propose to remove 3 teeth. That's this girl here, to also have an efficient design for eating ice cream. So with this, I am at the end of my talk. So let me remind you some of the key points. I mentioned the fact that you have a critical junction site that explains the transition in adhesive wear mechanism, that's functional material properties. I told you that the tangential frictional work predicts without fit parameters the initial debris size at the asperity level. This opens a path to deterministic wear coefficient K, because K is not a probability, it's deterministic for us. I've shown you also that third bodies and competition between ductile and brittle mechanism yield self-affine surface roughness that naturally comes out of our model. And I forgot to say when I showed the slide from Enrico Milanese that the amazing story, the self-affine properties that emerge from our calculations are independent of the initial conditions of our system. And we are actually doing experiments on the roughness evolutions, and I've shown you at the end a patent application to an innovative design emerging from interactions between nearby microcontacts. With this, I thank you for your attention, and I'm looking forward to answering your questions, if any. Thank you.